what is unique about keratin and modification of that, we have different functional groups, and they can be present either positively charged or negatively charged at the same time. So we can actually absorb multiple contaminants at the same time. Even if you take any pH, there will be some positively charged, some negatively charged. And so based on their positive and negative charges, they can attract different type of contaminants.
Welcome to the Project Report. Join your host, Elyse Dzenick, as she sits with researchers and highly qualified personnel working on FES-funded research. Explore what they're working on, why it matters, and what's to come.
Today we're sitting down with Dr. Aman, who works at the University of Alberta's Department of Agricultural, Food, and Nutritional Sciences. Thank you so much for joining me today to talk about decontamination research. So you're looking at using keratin biopolymers that are derived from chicken feathers to create biopolymers. What exactly are keratin biopolymers?
So keratin biopolymers are the polymers which are proteins in nature, but they're coming from feathers. So poultry feathers are or byproduct of poultry processing. They take the chickens, they process them, meat is used, but feathers go to the landfill. So that's a byproduct. We can make use of those to create adsorbent materials, which can be used for water treatment, for tailing consolidations, and feathers contain almost all keratin. So that's a great material. My lab actually works on waste utilization, making materials from by or co-products. Our bigger goal is to focus on circular economy so that we can recycle back some of the waste materials and make some useful products out of that. We currently have a linear economy model where we produce things, we use them, and we discard them. Circular economy model is where we recycle or reuse those materials. Our target is to take the waste materials and upcycle them and use them for different type of applications. We are also looking at desorption and reuse of these adsorbents. So we used it once, we have the adsorption of materials on the surface, we remove those, activate it, and reuse it again, so that we can use it multiple cycles and make use of this for a longer period of time.
Your technology works on both adsorption and sorption. What are the difference between those two?
Yeah, so sorption is a broader term where we are talking about both adsorption and absorption. So adsorption is surface phenomenon. If something sticks to the surface, for example, if we have something sticky and dust sticks to it, that's a adsorption. But absorption is when something gets into the material. So absorption is a general term which is used when we really don't specifically focus on adsorption or surface attachment, but there are some other contaminants which can get in there. So that's why we use absorption as a general term. I think this kind of materials, more accurately, we can say adsorption, because we functionalize the surface where the contaminants will be attaching. But because we don't know 100% adsorption is taking place, therefore general term absorption is used.
So the end goal is wastewater decontamination and soil remediation, that's correct. How do you get there, I suppose?
Yeah, keratin or feathers itself, this is a cross-linked protein. Therefore, the feathers are stiff and strong, but still lightweight. What we do is we take the feathers and open up that cross-linked protein. Protein is generally a heterobiopolymer. What does that mean is we have amino acids linked together like beads in a string. And so those beads or amino acids have different properties. So they are linked together to make a larger, big macromolecule we call a biopolymer. Those biopolymers are cross-linked through some linkages. We break those linkages, we open the biopolymers, unfold them, and now they become adsorbent to remove different kind of contaminants. We can remove heavy metals, for example, we can remove naphthenic acids, and they can also act as flocculants to consolidate the tailings. As you know, for oil and sand processing, they use water to extract the bitumen, and after that, water is put into tailing ponds. And now we take the cap water or top water to recycle it, but the ponds themselves, they do not consolidate. So we use these as a flocculant to consolidate it. So there are two applications. One is to remediate the water, and second is to consolidate the tailings.
Selenium is one of the major contaminants in the oil and gas industry. So far, many methods have been developed to remove that selenium, but the problem is they are not cost effective. So in order to develop a new method which is very cost effective and can be derived from renewable resources, we are using chicken feathers. So chicken feathers are basically consist of more than 90% of keratin proteins, but we have to modify them to improve their absorption capacity for heavy metals. But in order to improve their absorption capacity, we have to have break the bonds which are present in the keratin. After that breakage, we are introducing different type of nanoparticles in that keratin proteins to improve their absorption capacity. So once those nanoparticles interact with the keratin proteins, it means there are many type of functional groups that are being exposed after modification with those nanoparticles.
How do you get the biopolymers to target specific heavy metals or certain contaminants in each of the situations that you're applying your biopolymers?
Yeah, that's a good question. So we take the base keratin and we functionalize or modify it. And as I mentioned before, because keratin is made up of different amino acids, they have different type of functional groups on the surface. They are hydrophilic or hydrophobic. What does that mean? Some like water, some don't like water. So depending upon the contaminant, we can tweak them to make either more hydrophilic or attracting certain type of contaminants. Or if we want to remove, let's say, naphthenic acids or other stuff, we can make them other way around. This is a tweaking process. We call it surface modification or functionalization. And using that method, we can use the same base material for different type of contaminant removal.
We are hoping that we can prepare something that is cost effective and can be applied in large scale, especially for developing countries which do not have the ability to use expensive and advanced technologies. In this case, what we are doing, firstly, we are preparing the magnetic nanoparticles. And the reason why we are using these magnetic particles, we have run into a lot of studies that they use iron for extracting the selenium from wastewater. So we were hoping that we could combine this with chitosanes and then with keratin to create something that is even more effective and efficient. The reason why we are using keratin in this case, firstly, we want it to be environment friendly. That is why we're using keratin, which comes from renewable resources, in this case from chicken feathers. And also keratin has shown that it does have different functional groups and has the capacity to capture different heavy metals. And now combining it with iron that has showed some potential in capturing other heavy metals or selenium, we're hoping that this will increase it overall and it can be applied in large scale.
Is there cost benefit to using keratin in your biopolymers compared to like current materials?
In terms of cost, I think keratin is a cheap material. It's a waste material. So if there was extraction process, then there will be cost involved. But because we don't extract it, we take the keratin, we dissolve it, exfoliate it, and make adsorbent material. So we have less cost associated compared to, for example, chitosan, which is extracted from seashells or marine waste material. Extraction costs are associated with that. Chitosan also is a good material, but keratin itself has really unique properties because of different type of amino acids. Chitosan has a unique chemistry because it is a homogeneous material, but keratin is a heterogeneous material because of different type of amino acids. So due to those different functionalities, its ability to attract contaminants is much better, higher in terms of cost because it's a waste material coming from the poultry processing plants, and they were really happy if we can make use of that. So that will be an advantage.
Can you remove multiple contaminants at once with your biopolymers?
Yeah. So that's the advantage of these biopolymers, especially the protein-based biopolymers, compared to conventional polymers or adsorbents. They have one type of functionality where you already know that they will be taking either, if they're negatively charged, they will be taking positively charged contaminants. If they're positively charged, they will be taking negatively charged contaminants. So with this protein, we have a unique ability for different type of charges at the same time. So by just tweaking the pH, we can create different type of charges at different amino acids. So it becomes like a multi-absorbent material because it has different amino acids at different sites. And so they can have positive, negative, they can be polar, they can be hydrophobic. So therefore, it can absorb multiple type of contaminants. For example, we have seen we can remove both positively charged and negatively charged metals. We can remove naphthenic acids. And so that's a unique material which actually attracts different contaminants at the same time and without any modification, because if you have conventional material, it will be either positively charged or negatively charged, either polar or non-polar. So in that case, you know that it will be attracting certain type of compounds or contaminants.
This setup is continuous reactor system. The flow is completely based on the gravity. So it has two tanks. One we specify for the ulcer and process water. Another one is we use it for the simulator water. So we simulate it according to the different composition of the water, different metal concentrations. Then we pack keratin material, whatever we prepare, pass it over through the column. And once it's done, then we have to take the sample out after every 15 minutes. And then we need to plot a breakthrough curve. Based on that breakthrough curve, we need to plot from there. And we also did some modeling as well, but we plot the breakthrough curve. From breakthrough curve, we can estimate how much the adsorption capacity is of each metal. And we can also calculate how much adsorbent is needed for the for the treatment of the water.
When did you start working on water filtration and decontamination?
Yeah, so I started working on water filtration and decontamination about 15 years back. And this started with call from Grand Challenges Canada. And they were looking at finding a solution for removal of arsenic from water in developing countries, because arsenic is a big problem in developing countries. And this is present in all the groundwater, and the people there use groundwater for drinking applications. So at that time, I proposed this approach of using keratin to remove arsenic. And so we started working on that. That was supported through Canadian Rising Star Award. And so we started working on that. And then we knew that it doesn't only target arsenic, it does target or can remove other contaminants as well. So we started looking at other contaminants. And then from there, we moved into water, which is more contaminated, oils and process affected water. And then we started looking into tailing consolidation. So by understanding the material more, we were able to tweak it better and make use of in different type of contaminated waters or even tailing.
So you have quite a few partnerships with your work and have had some significant partnerships over the years. How do they fit into your work? And can you explain a little bit of your collaboration and where the collaboration comes from on both parts?
I collaborate with quite a few colleagues on campus. I'm collaborating with Dzenick, where Tariq is a soil chemist and understands soil chemistry better. He also works on water tailing or water using other approaches as well. And then I collaborate with Nate. I collaborate with Mortada Sadrzadeh. So Mortada has membrane technology-based approach to decontaminate water. Through this new approach, we are combining both adsorption and membrane technology so that we can treat different type of waters more effectively. One of the challenge with biopolymers or adsorbents is that they do not effectively remove microbes. And so membrane technology can remove microbes as well. It's like an approach where we can combine the two technologies and really get clean water.
That's really cool. In terms of, you had mentioned drinking water earlier. It sounds like you're taking the magnet sort of aspect of the adsorption technology that your research has offered and combining it with the membrane technology of Dr. Mortada Sadrzadeh to get essentially like a magnet and a filter to then get really clean water for drinking?
Yes, that's the approach.
So you've taken us on a journey of how you got here. What's next for you and your lab and this technology?
Our next plan is to commercialize the technology. We have industry partner. We are working to develop a system where we can combine both adsorption and membrane technology. And once we develop that system, we have industry partner who is willing to help us build a prototype. And then we plan to give that prototype to different industries where the contaminated water is a problem. And so we get feedback from them and we incorporate that feedback. Another approach is that those people who are testing probably will become early adopters of the technology. So we start then commercializing this technology.
Is there anybody else that you would like to mention for their support?
Yeah, I think Future Energy Systems is for sure one of them. We've got funding from NSERC. We have MITEX. We also have industrial partners. And Grand Challenges Canada was the first one to fund. So all the funding agencies and also the partners.
It's always a collaborative effort.
Yeah, collaborative effort, yes.
Yeah.